Welcome to EMR Physics. I am Raju, NCERT 10th Science. We are solving the numerical problems given in Chapter 10, the human eye and the colorful world. In this video, we are going to see how to solve the numerical problem 7. It is a book bag problem. The problem is make a diagram to show how hypermetropia is corrected. The near point of a hypermetropic eye is 1 meter. What is the power of the lens required to correct this defect? Assume that the near point of the normal eye is 25 cm. This is a given problem. In this problem, the near point of a hypermetropic eye is given as 1 meter. But the near point of a normal eye is 25 cm. What is asked? We have to draw the diagram to show how the hypermetropia is corrected. Next, we have to find the power of the lens required to correct this defect. First, we have to draw the diagram. Next, we have to find the power of the lens required. Now, let us see how to solve this problem. For a normal eye, the near point is 25 cm and the far point is infinity. If a person is suffering with hypermetropia, then he can see the far objects clearly. If the object is at infinity, then he can see it clearly, but he cannot see the near objects. Suppose if the object is at 25 cm, this is a normal near point. If the object is at 25 cm, then the eye will form the image behind the retina. Since the image is formed behind the retina, the eye cannot see it clearly. If the near point is shifted to a longer distance, then the image will be formed on the retina. So, the near point has to be shifted. To do this, a convex lens can be used. Convex lens can shift the near point to a longer distance. It forms a virtual image at this distance and the eye can see it clearly. In our problem, it is given that the far point of a hypermetropic eye is 100 cm. Therefore, the virtual image has to be formed at 100 cm. If the object is at 25 cm, the convex lens has to form the virtual image at 100 cm so that the person can see the object clearly. We have to calculate what is the power of the convex lens to be used to do this job. That is, if the object distance is 25 cm, then the image distance has to be 100 cm. We have to find the power of the lens to be used to shift the near point. Now let us do the calculation. In the given problem, the first question is we have to draw the diagram to show how the hypermetropia is corrected. By using a convex lens, we can correct the hypermetropia. If the object is at 25 cm, then the convex lens forms virtual image at 100 cm so that the hypermetropic eye can see the image clearly. Therefore, if the object distance is 25 cm, the object is in front of the lens. Therefore, we have to put a negative sign here. Virtual image has to be formed at 100 cm because the near point of the hypermetropic eye is 100 cm. It is given in the problem. So, the image distance is given as 1 meter. Since the image is formed in front of the lens, it is minus 1 meter. This can be written as minus 100 cm. So this is given in the problem. If the image is formed at 100 cm, then the eye can see it clearly. So we have to use a convex lens of suitable power. We have to find the power of the lens to be used. First, let us find the focal length. If we know the focal length, then we can find the power. This is the second question. We have to find the power of the lens to be used. Focal length can be determined by using the lens formula. The lens formula is 1 by f is equal to 1 by V minus 1 by U. We know the value of V and U. If we substitute, then we will get this is equal to 1 divided by what is V? V is minus 100 centimeter minus 1 divided by what is U? U is minus 25 centimeter. All the values are in centimeter. Therefore, we will get the focal length in centimeter. This is equal to minus 1 by 100 minus of minus plus 1 by 25. This is equal to, if we take 100 as LCM, we will get minus 1 here. In 100 there are 4 25s are there. Therefore 4 into 1 is 4. Here we are having plus. So plus 4. This is equal to minus 1 plus 4 is 3 divided by 100. This is 1 by F. If we take the reciprocal on both sides, we will get F is equal to 100 by 3, which is equal to 33.33 centimeter. Once if you know the focal length, then we can easily find the power of the lens. Focal length F is equal to 33.33 centimeter. We have calculated this. Let us convert this to meter to get the power in diopter. Diopter is the unit of the power. So this is equal to 33.33. 1 centimeter is equal to 10 to the power minus 2 meter. That means we have to divide 33.33 by 100. If you divide, we will get this is equal to 0.33 meter. So this is the focal length in meter. We are converting this in order to get the power in diopter. Power is equal to 1 by focal length. Therefore, this is equal to 1 divided by 0.33. 1 divided by 0.33 is equal to 3.0. This is the answer for the second question. We have calculated the power of the convex lens to be used. If you find this video is useful, please subscribe the channel, share it to your friends. Thank you for watching this video.